Hi, and welcome to this demonstration of how a feed-forward neural network learns a circular dataset using different activation functions. Activation functions play a crucial role in determining how a network transforms and learns from data. For this demonstration, we'll focus on two activation functions, tan and sigmoid. Another popular activation function, ReLU, is also available. ReLU, or rectified linear unit, outputs 0 for negative values and passes positive values unchanged. It is highly efficient and often used in deep learning due to its computational simplicity and fast convergence. However, ReLU can struggle with nonlinear patterns like the circular dataset. While we won't demonstrate ReLU in this video, it's important to know its strengths and limitations. Instead, we'll dive into tan and sigmoid to observe how they perform with a higher learning rate and fewer training steps. So our dataset consists of two classes distributed in a circular pattern. The goal is for the neural network to learn a decision boundary that separates these two classes. For both examples, we're going to use a learning rate of 0.7 and 50 training steps. The training steps limit the time that network has to refine its decision boundary, and the learning rate means that the model takes large steps when updating weights. In this first example, we're using the tan activation function with 0.7 learning rate and 50 training steps. Let's try and visualize. So tan outputs values between -1 and 1, which allows it to handle nonlinear relationships effectively while maintaining balanced gradients. So for the 3D scatter plot here, in the hidden space, the features are transformed by the tan function. You can see how the values are distributed smoothly across the range of -1 to 1, which helps the network adapt to the circular pattern. Here in the middle plot, the decision boundary begins to emerge, but due to the limited number of training steps, it remains underdeveloped. With more training, tan would refine this boundary further to wrap around the circular dataset. And the gradient visualization shows that updates are balanced and consistent across the weights, reflecting tan's smooth gradient behavior. So overall, tan is particularly well suited for nonlinear datasets like this one. However, with only 50 training steps, it doesn't have enough time to fully optimize the decision boundary. Now we can move on to the sigmoid testing. And for this, we're actually going to be doing the same learning rate and number of training steps. So first, let me type in sigmoid and then 0.7 learning rate and 50 training steps. So sigmoid actually outputs values between 0 and 1, which is useful for probabilistic outputs. However, it tends to saturate for very large or very small inputs, leading to smaller gradients. In the 3D scatter plot here, the features are limited to values between 0 and 1. This restricted range makes it harder for the network to capture complex patterns compared to tan. And the decision boundary here in the second plot is less refined than in the tan example. The vanishing gradients of sigmoid slow down learning, especially with a higher learning rate like 0.7. And finally, the gradient visualization shows sparse and smaller updates. This behavior reflects sigmoid's challenges with maintaining strong gradient flow, particularly in the later stages of training. So while sigmoid is useful for binary classification, it struggles with the circular dataset due to the vanishing gradient problem and its limited range. So in this demonstration, we saw how tan and sigmoid functions or activation functions perform under identical settings with a higher learning rate and fewer training steps. Tan was better suited for the circular dataset as it maintained balanced gradients and captured the nonlinear pattern effectively. Sigmoid struggled more due to vanishing gradients and its limited output range, resulting in slower convergence and a less refined decision boundary. Thank you for watching, and I hope this demonstration helps you better understand how activation functions influence neural network performance.